Special revision for a fiber reinforced polymer strengthening project, and our speaker is Gregg with Milliken Infrastructure Solutions.
Thank you, Dave, and thank everybody for sticking around to hear me talk on a rather dry subject like writing a special revision. I have a little bit of expertise in this area because, as Dave mentioned, I just recently chaired ICRI 330, and one of the things, it only took us 6 years, but we finally did produce a guide specification. Essentially, it's a special provisions written for buildings, but it is a very nice tool that is at your disposal. So I'm going to spend a little time this afternoon talking about where I see DOTs using FRPs. I review hundreds of projects every year. A little bit on the design considerations, and then get right into specification concepts, things that you really need to take away with you when you're writing your special provision. So I don't even need to cover this. I think this whole session's been on FRP. Basically, we're talking about externally bonded reinforcement. Reinforcement that's applied to an existing structure to increase its capacity. The common strengthening forms that you've seen today are, for the most part, I'm going to be talking mostly about the wet layup systems. This is what the ICRI guide spec covers, but there are others as well. So for the most part, you're talking about unidirectional carbon fiber systems. Fiberglass is not used a lot. I'd say initially it was, but just over the last 25 years, carbon seems to have predominantly dominated this market. And that's probably because the cost of the carbon has dropped as well, and it results in less labor because you're usually putting out fewer layers. There's multi-directional fabrics, which are not very common. Most suppliers don't even stock those or inventory those. Then there's pre-cured products. David referred to carbon fiber plates. Dave White from SEEK in his presentation. That is a form where the epoxy and the fibers are combined off-site to produce a plate, or in this case, a bar, perhaps, like a carbon fiber rebar that is used for strengthening, or a relatively new product on the market are carbon fiber strand sheets, which look like little sushi mats that you'd roll up sushi with, like bamboo blinds, but made with carbon fiber micro rods. And these are predominantly used right now to strengthen steel structures. The carbon fiber bars, and I have an acronym up there called NSM. I'm sorry I didn't say what that was. It's near surface mounted reinforcement. So if you're trying to strengthen the negative moment region of a bridge deck, you typically don't want to be bonding fabric or plates to the top of it and allowing traffic to drive over it. So what contractors will do, they'll cut very shallow slots, like 1/2 inch by 1/2 inch, fill that slot with an epoxy resin, and bond the carbon fiber bar into that. So they recess the reinforcement. It does the exact same thing that the fabric does. Where I see a lot of DOTs using FRPs, and Dave, you tell me if this is right or not, but my impression is that DOTs are slowly, over 25 years, discovering these materials. They are, the majority of almost all projects that are done in the United States, I would say, are in buildings and industrial facilities, probably 75 to 80%. Very few, relatively speaking, are done on bridges. But what we see is pier columns, either for seismic retrofit or doing concrete repairs, as the gentleman from TxDOT showed, and then wrapping those. For confinement, pier cap strengthening, for shear and flexural upgrades, also for addressing corrosion-related deterioration, but if you have additional loads. Girder shear strengthening. This is using carbon fiber U-wraps to wrap around the existing, either a rectangular concrete girder or an AASHTO girder to strengthen it for increased shear capacity. Impact girders. You see a lot of these types of applications. Seems like Texas has more than most, but actually you see these in almost every state. Deck strengthening, both positive and negative moment. This is an application where the near surface mounted reinforcement is used to go ahead and increase the negative moment strength of the deck slab on this arch bridge in Spokane. So it was actually the AASHTO T6 committee could have checked it out last year. I'm starting to see more and more projects like this right now on the West Coast, California, Oregon, Washington, where barrier systems are being replaced on older bridges, and in doing so, the new barriers are higher. They're designed to carry higher impact loads, and that's stressing the deck, putting more tension on the deck, pushing it out, and also overturning moments. So these are addressed by using a near surface mount of reinforcement in the top of the deck, as you can see here. It's just an arch slab strengthening that was done. Actually, it's concrete repairs are done, and it was strengthened for additional loads using carbon fiber. Protection. This is what I would classify as it's a non-structural application of FRP. The concrete repairs are done using good concrete restoration techniques, and then it is wrapped, in this case, with a fiberglass FRP and epoxy-based system to go ahead and provide additional protection and confinement to those types of repairs. And one example of a steel strengthening project where, in this case, the detailing on the original truss bridge wasn't very good. The deck was cast right up against the diagonal members where they penetrated. It was a source of corrosion. Once the corrosion was discovered, in this case, the corrosion was cleaned off, sanded, and surface of steel prepared, and carbon fiber strand sheets. These are ultra-high modulus carbon. I'll show you what that means in a second. Were bonded to the steel to go ahead and basically replace the cross-sectional area that had been lost. This kind of gives you a list of where I see, in my experience, DOTs are using FRPs for a combination of both structural applications and non-structural applications. So before we get into the special provision, we need to talk a little bit about some basic design technique, principles, I guess I'd call them. Dave showed a very similar chart in his presentation. This just compares the various types of fibers. It shows you how the ultra-high modulus carbon compares to the traditional carbon that's used on the majority of all concrete applications. And you can see these are all brittle materials. They don't yield like steel rebar or post-tensioning tendons. So any sort of designs that are done with these materials have to go ahead and take that into account. Compares to grade 60 bar and PT. Now these are bonded application. Well, there's two types of applications with FRPs. There are what are known as bond critical applications, where the FRP has to be bonded, well bonded to the concrete for it to work. If it's not well bonded, it's not going to function. Then there's contact critical applications like wrapping a column, where it doesn't have to be bonded. It has to be an intimate contact for it to work. You can't have gaps and things like that. Now with bond critical applications, FRPs have what's known as an effective strain. You can't put on 10 layers of FRP bonded to concrete that has a 4,000 PSI compression strength and expect it to rupture. That's just way too much material. What's ultimately going to happen is the more layers that you add in, say, at the bottom of a slab and you flex that slab, your failure mode's likely going to be debonding of the concrete or failure in the cover concrete itself. So all the design methods that are out there right now, ACI 440, I'd say, is what we call the Bible of the industry right now. Make sure that when you're designing, you get something very similar to this, which basically says the more layers that you add, the less and less effective each subsequent layer gets. So you're not going to see projects where you're using 10 layers in a bond critical application. It's just not possible. You're going to fail the concrete well before that would ever happen. And it's not going to be a cost-effective approach. So one thing you need to keep in mind is in bond critical applications, the stiffer your laminate, which is essentially modulus, thickness, and the number of layers, results in a lower effective strain. And the same is with shear. I mean, shear strengthening can be accomplished. Well, unfortunately, that's not showing up the way it shows up here. There's T-beams there. Just imagine a T-beam. The best way to shear strengthen is obviously completely wrapping the beam, but that's not possible because slabs are always, or decks are always supported by beams. So you're typically going with U-wraps. And it's the same thing here. You're limiting the strain in the FRP. You never take the strain up to ultimate in your design. With With shear strengthening, you're limiting it even more to a very small number, 0.004 strain. Steel yields at 0.002, steel bars. FRP fails at like 0.015, carbon fiber. Because you're limiting it to such a small amount, the stiffness is so important in your calculations. So we'll see how that all comes out to play when you are doing your special provision. Same thing with axial. Once again, you're limited to strain to 0.004, and axial, essentially you're wrapping a column. All the fibers are horizontal. And you're trying to get additional axial capacity out of a column. And the way you do that is wrap it and confine it. So as that column compresses, it starts to dilate and want to bulge, and that confinement prevents it from doing that, allows it to see a higher confined compression strength, which is what you use in all your design calculations. So there are several sources of information out there when you're doing a project, designing it and then detailing it and then writing the special provision. ACI 440 has been around the longest. It came out back in 2002. Just recently had added seismic provisions just in 2017. It covers NSM. It's been around so long, and it has a strong basis of research that has gone behind it. There's a lot of academics that sit on the committee. I mean, our committee in ACI has probably 150 members that all contribute to this document. The majority of all projects use this as the basis for design. You have AASHTO has a guide spec as well. That's been around since 2012. I say beware. The design methods and design equations in that document produce different results from what ACI 440 produces, which is surprising to me because it seems as though they should at least produce the same member strengths for the same type of design. And the only thing that might be different would be fee factors and things like that that would be more applicable to bridges. When you're specifying, and I've seen this done by some DOTs, where they'll specify ACI and AASHTO. Don't specify both. You can only specify one. Here's an example. AASHTO has an equation that's kind of hard to see on peeling. You know, this is actually a very good thing that, we know from aerospace design of composites. Peeling calculations are very important, but this particular equation requires you to know what the shear modulus of your resin is, which no supplier reports. It requires you to know what the bond line thickness is. These are all very important parameters in a theoretical and academic sense, but not in the field. How do you measure bond thickness in the field? How do you even design for something like that? So until these issues are corrected with AASHTO, I would encourage you to look at both and design your bridge accordingly, but I would really encourage you to use ACI as your design basis until this is corrected in T6. And this gives you an example. Ran a project where the engineer and DOT actually specified both ACI and AASHTO for a pier cap, and so it's shear strengthening. So we looked at, in this case, it's a U-wrap and a complete wrap, and it shows the two different values that you're getting for shear capacity. So, if I'm a contractor or a supplier, I'm going to use the one that gives me the best chance of getting the job. Don't allow this to happen. Never specify both. And then, of course, there's ICRI Guide 330, which is actually a very good document. It's a Word document that you can purchase from ICRI in Word format, and you can download it, and then you can edit it. It's about 40 pages. It's not a 40-page special provision. It's 30 pages of commentary on practically every single paragraph, and you edit it to address the issues that you have with your particular project. So as I get into specifying and detailing, let's just look at what the typical phases in a project might be. And this is true for buildings or bridges, it doesn't matter. You do a condition survey, you analyze the structure to determine If anything needs to be strengthened, what requires strengthening, go ahead and determine if FRP is feasible, design it, contractor bids it, submit shop drawings, calculations, you review those submittals, the project gets executed and inspected. On the majority of all projects, certainly building projects, the part in orange is typically delegated to the contractor and their specialty engineer, who actually does the design calculations for the FRP, produces the shop drawings, and does the submittals. It's very important, though, as the engineer of record, that there's certain things that you need to be doing. One is you're always going to be responsible for the condition assessment of the structure. You're always going to be responsible to determine if what needs to be strengthened and where it is, and telling the engineer and the contractor what that is. And you have to be responsible for verifying if FRP is even a good candidate. And there's equations within both AASHTO and ACI 440 that will help you determine if FRP is even a good candidate for a particular project. That's your responsibility. Once you get past that, then you can go ahead and delegate, provided you detail and specify the performance requirements, the FRP design. And then you're just reviewing the submittals. You need to decide if the project's going to be prescriptive or performance, and where are you going to communicate the information. I've seen it as a separate spec, a special provision. I've seen it communicated as drawing notes in the general note section. I've seen a few notes added to the FRP detail. It just depends on how complicated your project is, but you do need to communicate certain type of information. And that's what we're going to be talking about. So, verifying if FRP can be used. These are the equations. Basically, what they are telling you is that your existing structure has to carry some reduced amount of your factored loads without FRP. So your new, you basically, for ACI, that's 1.1 times your new dead load plus 0.75 times your new live load. And you have to compare that to your existing capacity with no FRP. If you can meet that requirement, AASHTO has a very similar one. Chances are it's a very good application for FRP. And I mean, the last thing you want to do is put FRP in your drawings, delegate the design, and all of a sudden the contractor's coming back to you saying, you're tripling the capacity of this beam. It's not possible to do that. No FRP engineer is going to sign off on that. So then the next thing, determine and understand, is your project going to be bond critical or contact critical, or a combination, or maybe both. If it is a contact critical application and your concrete strength is less than 2,000 PSI, it's not a good application for FRP. Because now you're trying to bond to a incompetent substrate. It's not going to be able to handle anything bonded to it and transfer forces. Where do you communicate this? Make a decision and then specify accordingly. Prescriptive. Like I said, I don't see this done. Caltrans does this, actually. Too prescriptive, maybe. But very few DOTs, very few building engineers are totally prescriptive. It's usually some combination of performance and prescriptive, but usually if it's a structural application where you're trying to increase the capacity of a member, that's likely going to be a performance spec where you're delegating the design to the contractor and the FRP specialty engineer. If it's a Spall repair that you're confining, putting some FRP over the top, and it's really a non-structural repair, then you can prescribe all you want, because there's really no design involved at that point. But if you are prescribing, this is all the information you need to put on the plans. Number of layers, where they're going to go, the details, how long those are, and you need to specify the material properties that you base that design on. And once you do that, then a contractor can come in and go ahead and say, I have a product, these are the materials that you use, we want to use, this is the product that we use, and here's the equivalent number of layers to meet the design. Performance specs are much more common, as I mentioned. Here, you're going to be specifying all the properties and all the dimensions and all the concrete strength and the framing plan and all the other, everything that you use to determine that there was a deficiency to start with, that needs to be on the plans. And if you don't know what it is, you've got to go ahead and commit on something. You can't, I mean, I've seen projects where and this is, I'll say these, when I talk to building engineers, they say that DOTs do this all the time. But now I'm talking to the DOTs, I'm gonna say building engineers. Actually, we see it more with building engineers. Where they'll show a beam, and they'll say, I want to increase capacity 20%. We're like, what's the dimensions of the beam? We're like, we don't know. I'm like, well, you have to tell us that. And how much steel is in the beam? What's the existing capacity? How do you know you even need to go up 15%? These are things, everything that you use to calculate that capacity and determine there's a deficiency needs to be on the plans. So you're going to specify member requirements, the performance requirements. And there's several ways you can go about doing this. You can put all that information on the plans. You can go ahead and say, I want to increase the capacity of this beam 20%, or I want an additional 25 kips of shear capacity. Or you can say, I want you to provide additional flexural capacity on the bottom of this slab that's equivalent to number 4 bars at 8 inches on center. You know, any one of those are acceptable, but you need to specify the design method that will be used to go ahead and calculate that, like ACI or AASHTO. This is the other information, as I mentioned, everything that you put in, the engineer, the FRP engineer will use for the design. Now, when you're writing your special provision, you're going to have a section on submittals. Only specify submittals that you actually will review. You can specify hundreds of test reports and things like that, but if they're not to be reviewed, then there's really not. One of the things that you will definitely require is product technical data sheets on the fabrics or the NSM bars, everything that you're going to use. Certain test reports that might be applicable to your particular project. You also might specify like shop, well, of course you're going to want shop drawings, engineering calculations. And one of the things, and of course, this doesn't really happen with DOTs, but I do see it with building engineers. A lot of times the manufacturer will get in, talk to an engineer and say, you know what, I want you to go ahead and specify that anybody who's going to be submitting as an alternate, submit sealed calculations and shop drawings with the bid. And that's something that you obviously don't want to be doing because you're essentially limiting yourself to just one contractor. Payment basis and warranty. Be real careful with your units and bid tabulations with this particular material. Most of the time I see lump sum. That seems to be pretty reasonable. A lot of times the units might be square foot. Well, square foot of what? Is it just the coverage area? Is it just one layer, or is it square foot of 3 layers of just, is it the material? So you need to really be prescriptive as spelling out what that unit is that you want your unit basis on. And avoid really complicated units. There's one DOT in particular that actually has to put a design equation on their plans to tell you how to calculate your units for doing your bid, which that's a little too complicated. What this means is when you're going back and looking at bid tabulations from one job to another, you really need to know how many layers went into that job. It's going to be hard, at least for the foreseeable future, to be able to compare bid tabulations from job to job. Warranty, most manufacturers, contractors offer a year. That could be extended as needed, but avoid putting in very vague language like it should last 25 years, or I want a 50-year warranty, because that usually will invite desperate contractors, desperate suppliers. Okay, so if you get anything out of this presentation, this is what I need you to get out of it, is understanding technical data sheets. Every manufacturer that supplies FRPs publishes their data in technical data sheets, and hopefully they're publishing design values, which is the average of 20 or 30 tests subtracting 3 standard deviations. which is a pretty aggressive way of doing it, but that's what ACI requires. What they'll also publish, and it's going to be hard to see here, unfortunately, is they're going to publish a section on fiber properties. These are the properties that basically of the fibers that David talked about in his presentation that are the input fibers into your particular FRP system. And then there's going to be a section on the laminate properties, the cured properties of the system. There's only one manufacturer that only publishes fiber properties because they normalize their properties to, well, they use the Japanese approach, which is essentially normalizing to just the area of the fibers and not the actual thickness of the laminate. For fiber properties, you never, let's see if that, you're not going to be able to see that, unfortunately. I think this presentation is available. Never use these for design. They're basically just average properties of the fibers. It's basically saying this is the grade of fiber that I'm using in my input. What you need to do is you need to use the properties where the thickness of the materials, the ply thickness is given. The reason you do that is because those give you, you can kind of see it here. That gives, that's the basis for design. Your ply thickness and your strength and your modulus form the basis of your design. Now the problem is, don't get hung up on your standard strength and modulus units, which are PSI, pounds per square inch. With FRPs, that's really not how you want to look at it. As I mentioned in those previous slides on design, you're always limited by your strain. And everybody reports their ply thickness slightly differently. Some manufacturers will actually, this is a wet layup system, so you're applying the resin in the field or with a machine, your thickness is going to vary slightly. But that's inconsequential because your fibers are what provide the strength, not the resin. So what's important is to go ahead and take the thickness and take that really out of the equation. And the way you do that is you take your values that are reported in PSI and multiply it by your ply thickness. And that gives you units in terms of pounds per inch per layer or per ply. The way to look at this is if I were to go ahead and wet out one layer of material and cut 1 inch of that and test it in tension, I might get 1,000 pounds. If I were to take that same material and pour a lot of extra resin on it and test it in tension, I would still get 1,000 pounds. So what we're doing is we're normalizing to the 1 inch width in both our modulus and our strength. And this kind of shows you how to go about doing that. So if you want to compare properties from one manufacturer to another, and especially from the one manufacturer that reports their properties using the Japanese approach, this is how you do it. You take your reported properties and multiply it by the ply thickness to get the units in terms of pounds per inch per layer. So when you're specifying, that's what ICRI and ACI, and that's what we encourage, is specify your properties, your modulus and your strength in terms of pounds per inch per layer. And actually, you can even specify your performance requirements in terms of, I need this many pounds per inch of stiffness per layer or per total. Do not over-specify on projects. I've seen projects where the engineer will do a very good job of specifying the tensile properties of the system, and then they'll specify like 10 properties for every single resin component that goes into it. That's over-specifying. All these systems have to be tested together. All these constituent materials are tested together as a system. So what is required for you to put in is ensuring that, specify that all the constituent materials are tested together. And just specify the properties, the design properties that are needed. Resin properties are not used in any, right now they're not used in any of the design equations in ACI or, well, maybe in that one peeling equation for AASHTO, but they're not used or considered right now in design. I would say be careful about allowing field thickening of resins. It's done. A lot of contractors do it, especially when they're using heavier weight fabrics to go ahead and keep them from sliding down columns or to hold them on. So just be careful about that. Some additional requirements that you might want to go ahead and specify. I'd say maybe 3 or 4 years ago, I would say don't specify ICC. ICC is International Code Council. They have an evaluation service. They write the building code, and they have an evaluation service that says, hey, listen, if your product's not mentioned in the building code, pay us some money, and we'll go ahead and evaluate it, and we'll tell you if it meets the spirit of the building code, and we'll write a little report. You can't do a project in California without that. But up until about 5 years ago, there was only maybe 3 companies that had that ICC report. Now there's enough, I'd say, where it's a safe way of doing it. The nice thing about specifying something like this is it spells out all the test requirements that almost all these manufacturers have had to go through. Durability testing, full-scale structural testing, and things like that. So, I think you'd be safe in using that. Installation techniques, as Dave mentioned, wet layup, secondarily bonded systems. The installation procedures are spelled out here. What you're really, like the repair of the substrate and crack injection and things like that, it's always going to be done in another spec item. The things that you need to keep in mind are installation-related considerations like this: temperature, humidity, whether the temperature is rising, age of the patching materials. Don't specify 28 days. Specify a patching material that's going to cure relatively fast and can go on with the FRP in a short order. So surface prep, most of this stuff is going to be in accordance with the manufacturer's recommendations, but you do want to specify a CSP3 for bond critical applications in accordance with ICRI, rounding corners, things like that. Application, wet layup or dry layup. Wet layup is actually wetting it out on a table or with a machine. Dry layup is taking the resin, applying it to the surface, and putting the dry fabric right in there. And these are some of the QC requirements that you'll be covering. Bond critical applications require much more, and structural applications as opposed to the non-structural. Witness panels, these are like concrete cylinders. Avoid specifying these if you can, because the contractors notoriously don't do a very good job of making them, and there's very few labs that actually test them well. The composites are not the easiest thing to test. Delaminations and voids, ACI has guidance on this, and this is what happens if you let temperature and environmental conditions run away and you don't manage that. The contractor doesn't manage it. In this case, you're putting a waterproofing membrane around a breathable concrete member. So as the temperature is rising, all the air inside those pores of the concrete start expanding and want to come right through that. You manage this by starting to do the work in the evenings or as the temperature is falling. This is the most important QC requirement, adhesion strength for bond critical applications. Bond a small steel puck to the FRP, pull it off, and ensure that you're failing in the concrete. And of course you need to fail above 200 PSI, but that's pretty easy to do even with poor surface preparation. You need to fail in the concrete. My concluding remarks are here. As the EOR, you need to analyze the structure. You need to go ahead and determine if FRPs are indeed an acceptable approach to fixing it. Decide on whether you want your spec to be prescriptive or performance. Always specify the unit tensile values. These are the values in pounds per inch per layer for both tension, strength, and modulus. Include all of the details that are needed for you to go ahead and determine that there was a deficiency to start with. Do not overspecify, and continue to use FRPs with confidence because they're used on thousands of projects every year. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.